So first of all, what is static analysis? If there is by any chance somebody who's not familiar, this is an instrument to analyze your program without executing it. So it reads the source code and makes some decisions based on what it understands about the source code. So we have some tools on the slides which are fairly popular. Probably everybody uses them. So Flakate, very popular. Pylint, very popular. I'm going on the second part about the technical, how to do this technically. I will talk about Pylint because this is what I use. We have Bandit, which is related to security stuff. That's a fairly new project coming from the OpenStack community. And we also have Coverity Scan, which is, again, for security-related scannings. This is a commercial project. It's not open source. So, okay. Okay, why do we need more tooling, more static analysis? All of these tools, they have a lot of rules inside of them, and if you have used any one of them, you know that it spews a lot of errors. So it takes you a lot of time to fix them and to maintain a project so that the tooling is happy. But I advocate that we need even more, and we need to have customized tooling. For example, what Lucas said about reading YAML files, and this can lead to security vulnerabilities. About 5-6 years ago, Ruby on Rails had this vulnerability, so you can send YAML because that's the default format in Ruby, and it can contain embedded JSON, and this JSON can be used to create some objects into memory, and it was bad. And the Ruby community, they patched Rails, pushed a new version, and 1 week after that, they had the same vulnerability in a different place in the source code. So they fixed this, pushed a new version, and a few more days or a week later, they had the same vulnerability in another place in the source code. Very bad time for them. So another example, what else? Something can change, or you can have interfaces which need to be maintained in the same way. One way to make sure that all of these rules are always other thing you can do is have a customized static analysis plugin, which will try to apply all of your rules and tell you, your source code is okay with the current policy, or it's not okay, you are breaking one of the many rules that you have in the company or within the team. For example, I'll give you a couple of examples. They are very easy, but you can make this as complex as you like. In Python, you can write documentation strings in this way. So all of these styles are valid. And in my team, only in the current project, we want to use the first style. So documentation strings only with 3 double quotes. We want to be consistent across every single file, every single documentation string that we have. For many reasons. One of them is just so that we don't like things to be different. We try to keep it as consistent as possible. So we have a customized Pylint plugin, which helps us discover these things, and if somebody tries to break this, the CI will fail. Another more practical example is coming from your frameworks and from your libraries. All of them have some best practices, they have some advices, and especially when you try to combine them, not everything works together, so you need to be aware of this. If you are using Django, it has the standard user model, and the documentation tells you don't use this model directly. So do this thing. Don't issue queries against the user model directly, and don't hard code this model as foreign key relationship. The reason is because there is a setting, and this model can be changed. And somebody who is installing your application can decide that they don't want to use the defaults, they want to use something else. This is what Django says. Another example is if you're using Django simple history to keep track of changes to objects, it works with signals. So objects.create, objects.update, this doesn't work. Another example that we use custom plugins for is finding places in the source code which can lead to problems. In this example, this is a problem with missing permissions. So at some point in time in our project, we kind of figured out that we have view functions which are missing the permission required decorator. So you can be a logged in user, don't have any permission, and still be allowed to perform some actions in the application. And we don't want to do this. So we wonder how many places we have where we are missing the permission required decorator. So we create a customized pilot plugin. It will examine the entire source code, and it tells us all the view functions or the class-based views which are missing the permission required decorator. Very easy. And we can also extend this to help us even more. So how we can extend more? Extend the permission required plugin to search for test cases for these permissions. So we need to make sure that everything that has to do with permission is adequately tested, both when the user has the permission and both when the user doesn't have the permission. We can also use some kind of naming conventions and make sure with a customized plugin that these permission labels which go in the decorator as strings, that there's no typo in there and they match the model name, for example. This can be done very easily. We have a lot of legacy source code in our application because it's 10 years old, and the way it was built was to create an application which maps on top of existing database schema. So we have these things here. We have autofields in Django where the name is not ID, that is the default, it has different name. And you don't always know this. We have database column as attribute in the field, which means in the database, the field has a different name compared to in the source code. And you have to remember two different fields if you, by any chance, need to work with the database. And that's ugly. We also have one-to-one fields in the application, and unfortunately, they don't work very well with the simple history library. So we have a constraint, don't use one-to-one fields. Which in another project is completely okay to use. So for all of these things, we do need customized plugins to help us. This is what we have right now. It's available on GitHub. We do have a little bit more as well, and I will talk only about this one. So we have custom business logic in the application where people can tag objects, and whether or not a new tag is created automatically can be controlled via settings and via permissions by the system administrator. There are some users of our application which have to they want to control the tag cloud very strictly, and only administrator to be allowed to add new tags, and the users are allowed only to consume them. There are other installations where everybody is allowed to create and edit and do everything. So for this, we have this method, which is a class method on the model. And you are not allowed to use this on that particular model. You cannot do tag.objects.get or create because it doesn't check the permissions. And we have a customized Pylean plugin, which will tell us, hey, you're not allowed to use the model manager method because it doesn't check permissions. So you're breaking business logic in the application, and that's a possible bug. So now I'm going to move on to the technical part. Hopefully you are convinced that you need to have your own customized tooling, which applies only to the current project, maybe to the current team, and sometimes more broadly to the current company, but not always. So two things are happening, which luckily for us, they are the same for every programming language, and they are also the same for every static analysis tool and for language interpreters, language compilers, so this knowledge can be transferred to other places as well. First step is parsing the input source code, also called lexical analysis or tokenization. And the second step is there is an abstract syntax tree which is created, and static analysis tool consume them. So parsing in Python does the following thing. You have an input, which is your source code, and that's a character stream. Each individual character doesn't have a lot of meaning. So we go through this box called lexical analyzer, tokenizer, parser, and we have the token stream, which is a different data structure with a little bit more meaning assigned to it. So we have keyword, we have variable, we have operator, we have number constant. So this is something which has more meaning and we can use it more easily. This is how you do tokenization in Python. We have the tokenize module built in. It provides the tokenize function, and the parameter to this function must be something which behaves like readline. So if you're working with files, then file object.readline is going to work. If you're working with strings, maybe wrap the string into a byte object or something else which provides readline, and work with that. Of tokenize is an iterator of token info tuples, which contain, this is a name tuple type, it contains 5 elements. So you've got token type as an integer constant, and then these things here in the brackets, these are constant names from the tokenize module, so you can use them in if conditions. You have token value as a string, start position, end position of this token within the current stream, and the entire line which is inspected at the moment. So all of this information can be used in if conditions to make some kind of decision, whether or not you are seeing a coding pattern that is a problem for you. Next thing is the abstract syntax tree, and as the name suggests, it's a tree structure. So if you don't know how that works, don't bother so much with it, at least initially. To be able to create plugins for static analysis tools, you need to know how to consume these data structures. You don't need to know how to create them. They are created automatically under the hood, and they are given to you to consume. If you have worked with HTML DOM trees, with XML trees, this is the same type of thing. So you have root node, you have children, you have siblings, they have different types. So the different colors are Python objects from different classes. They have different attributes, you can examine them based on the class, try to use some of the attributes, some of the methods. The way to create abstract syntax trees in Python is again very, very simple. We have this module which is built in AST. This is used internally by the Python language. And you have the ast.parse function which receives a string, and if you want to print this thing in the terminal, it's ast_dump. And it looks very ugly. You see what it shows. I will show you a better example. Next slide. This module is part of a standard library. It's documented. Take notice of this thing here. This is the documentation how to consume all the children nodes and their methods, their attributes. This is not part of the standard documentation. That's the only thing. And it took me a lot of time to find. But it's a good documentation. You also have another module for abstract syntax trees, which is called AstroID. This is not built into the Python language. This is an external dependency that comes from Pylint. Some tools use AST, some tools use AstroID, mainly everything that's based around Pylint. So these two modules, they are almost exactly the same, especially in the latest versions. They have done a very good job to try to match all the class names and all the attribute names and all the method names to be the same. So this is less confusion for us developers. But just be aware, you need to know which kind of module your tool is using. Again, we have a parse function which receives. You can print like this on the terminal. It looks a lot more better. So we see we have a module. It has a bunch of attributes which are completely non-interesting because it doesn't come from the file system. But this one is interesting. So we have body, which is a list. These are all the expressions in the module. And we have only one expression, so starts here, ends here. The expression is a call to a function. The function name is print. It receives a list of arguments. This list of arguments contains only one element, which is a string constant. So this is my example. You can use all of these to experiment in the interactive interpreter or create a small script and figure out how the tree structure or the token structure looks like for a particular coding pattern. So you can detect it later. AstroID is again very well documented. This is the documentation. 99% of the times what you need from this documentation is the reference to all the node classes, because you need to know their names to be able to inspect them. Next, I'm going to move into PyLint territory. Again, the good news for us is that everything that I'm going to show you, it's documented, and this is also the way how PyLint works internally. So everything inside of PyLint is implemented as if it was a plugin. So you can check out the PyLint source code from GitHub. You can read it for inspiration, or you can directly copy some classes and some methods and modify them later if this is easy for you. PyLint provides 4 interfaces where you can hook into. So this is your entry point into the source code examination process. The first one is the base interface, which provides open and close methods, and open is executed at the beginning when you start examining a module, and close is executed just before the end. Then we have the row checker interface, which provides process module, and notice it receives the result of asteroid parse. You can iterate over the entire module and all the children together and make some high-level decisions if you want to. This interface is very rarely used inside of PyLint. It's probably used in 5 different places only. And from what I have seen, it can be rewritten with the asteroid checker interface. So I don't know why it exists, it just exists. Maybe it's something historical. Nobody bothered to actually figure out why this thing is still here. Then we have the token checker interface, which provides process tokens, and this method receives the result of the tokenize function. So you can iterate over all the tokens, make some decisions based on that. And the last interface, which is the most powerful, and this is used most of the time, pretty much every error that comes from PyLint is implemented in this interface. This is the asteroid checker interface. So you need to implement visit underscore and leave underscore, and the actual name of this method depends on the class name of the node which you want to inspect. So if I want to inspect a function definition, then the method will be visit underscore function def. If I want to inspect a class definition, it's visit underscore class def. If I want to inspect a module, it can be visit underscore module or leave underscore module and so on. That's why you need to know the class names of these nodes. Another important thing is how these visit and leave methods are executed, and the order is depth first. And this is important because it gives you the opportunity to create a state machine within your plugins. So you can visit all the children nodes, and when you are leaving the parent node, you can be certain that all the child nodes have been visited. You have collected all the possible information which you can collect about this piece of code. And you can just apply some comparisons, some if conditions, and figure out, is this a problem or not a problem for you? So does this match your team policy or doesn't match your team policy? Now, this is how a PyLint plugin looks like. Very, very simple. PyLint is super stupid, and if you give it a module name, it will try to import this module into memory, and it will try to execute a function with the name register. So if it finds a function with name register and only one parameter, it will try to execute it. PyLint doesn't care what is inside of this function. After all, it's a standard Python module. What usually goes inside is this linter.register checker, and we create an instance of something which is called checker class. And I will show you how this looks like on this slide. So checker classes is the place where all the logic of examining coding patterns is. So in PyLint terms, plugins is usually something which registers the checker classes, and checker classes is something that does the actual examination. So this is how they decided to name things. All of this that you see is boilerplate code. So you just copy and paste this thing, and you have a checker ready to go. So give it a name, inherit from base checker. You need this attribute, this is mandatory, it's a tuple, and you tell it which interfaces you want to implement. You can implement one, you can implement all of them if you want to. You need a name attribute, this is mandatory, 99% of the time this is not used. This is only used if you want your checker class to read settings from .pylintrc file. You need messages dictionary, which holds all the error messages of your checker class. The key in the dictionary is this ugly alphanumeric message ID. This must be unique across Pylint and all the plugins that you want to enable, and this is also deprecated. So again, don't use it. It's just there because reasons, because it's open source and it's out there in the world. The value of this in this dictionary is tuple of 3 elements, so 1, 2, 3. First element is the short error message, which you see on the terminal when you run Pylint. The second member in this tuple is human readable message ID. This is what we use to enable or disable a checker. So for example, disable missing docstring. Everybody does this. And the last one, this is less known. This message, and this can be on several lines. And there are additional options to Pylint where you can display the long help, and it will tell you why this error is a problem, how to fix it. This is what you see when you Google for how do I fix this Pylint error, and you give the error name, and you see the answer. This is what you usually see. And the last thing you need to do is implement some of the methods of these interfaces. So in my example, because it fits on one slide, I implement close and just print an awesome message on the terminal. If you want to inform the developer after you've done a lot of if conditions and checking, if you want to inform the developer that there is a problem in this file, this is how you do it. Self.addMessage. First argument is the human readable message ID, and then you have several keyword arguments which can help you annotate where exactly this problem is. And Pylint will parse this information when it displays the result, and it will tell you, in this file on line 10, column 11, you have a problem. This is what the keyword arguments do. Important, how you load plugins with this option on the command line, or if you use an IDE, then you just need to pass this option to Pylint from the IDE. Important thing is usually you need to modify the Python path environment variable, because Pylint will not search for modules in the current directory. So this is what you need to do. And what I recommend, if you decide to go the road of creating your own plugins, put print statements in the register function, put print statements in your checker methods. If you can see this and this on the terminal, that means Pylint is able to find your plugin, it's able to register your checker class, and you are good to go. You can continue to refine your methods further. This is because there's no easy way to debug stuff from Pylint. So now I'm going to show you a few examples coming from our open source project. All of them are on GitHub. You can take a look at them. There are even more examples. All of them are very, very simple. I'm going to show you the most complicated example, which fits on 2 slides. So first thing, the documentation string checker. This is the essence of it. So this thing, it's not a global variable. This is just how I've written it. It's a class attribute which is initialized to empty dictionary in the beginning. So you can put this in it. Then we have process tokens, which goes through the entire token stream. And this is token type, token value, start position, end position, and the current line. And we look if the token type is a string, so it's some kind of hard-coded string in the source code, we just keep a reference to it in the dictionary. Key in the dictionary is the string without the quotes, and value in the dictionary is the string with the quotes, so the raw string. Then we have visit module, visit class dev, visit function dev, which are exactly the same, and they call this helper method. And very conveniently for us, so now this is token-based interface, this is asteroid-based interface. Very conveniently for us, all of these nodes, they have the documentation attribute, so .doc, which is already stripped from the quotes. And what we basically do is just dictionary lookup. And we take the raw value of this hard-coded string, we search whether or not it starts with 3 double quotes. If it starts with 3 double quotes, this is fine. If it doesn't start, then error for the developer, for our team to fix it. This is how we have the authentication user checker for Django. And again, this is very simplified. There's a reason behind all of this. So instead of looking for foreign key fields or many-to-many fields that link directly to the authentication user module, we look for hard-coded string constants. If we see this hard-coded string constant, we don't really care whether or not it's just hard-coded someplace else or it is inside of a foreign key field. We don't really care about that. Error for the developer, figure it out. And then we also do inspection of the import statements. So instead of trying to find user.objects.get and figure out whether or not what is called user in this module is this thing or something else, which can be done, but it's a lot more harder, we decided if I don't import the user model in the current module, there's no way I'm going to be able to issue queries directly against this. So I must be using the helper function provided by Django. So if I do wildcard import from this module, or I just import the user class, then there's possibility that I can use this class directly in queries. So don't do this, and everything will be fine. And the reason we do this is it is very simple. It gives us the opportunity to have very simple Pilot plugins, so we don't have to bother with them that much. This can be created in 5 minutes. And the other reason is it doesn't give us a lot of false positives. So we can tolerate these stupid plugins and not bother with fixing a lot of unnecessary stuff. Yes, sometimes we need to enable or disable the plugin for particular lines or for particular imports, but this is generally okay across the entire project, instead of spending days and weeks to create the best plugin that is possible. And here's how the permission checker looks like. It's entirely Astro ID based, so it does implement several methods. So first, we inspect the module. If this module is named views, so views.py on the file system, then we continue inspection further. We just keep this information in a Boolean variable. And you can have, depending on how you name things in your project, so this can be node.name equals to views, or ends with, or contains, or something like that. It depends on your naming conventions within your project. Then we have visit function def, which tries to examine function-based views. So is this a helper function within the module, or is it a function-based view? The way we decide this is to inspect the arguments, and if the first argument is called request, then it must be a function-based view. It doesn't matter whether or not it is a function-based view in reality. If it has a request as first parameter, then it needs permission required decorator, and that's it. And we call this function, this method, sorry. Then we have visit class def, which performs something similar for class-based views, but again, it does it even more simply. Instead of, so node.basis is a list of all the parent classes which you inherit from. Instead of examining their names and trying to figure out if they are Django views or not Django views, we just look for if this is not empty, then it must be a class-based view. Because in our project, this is the most simplest way to find class-based views. We do have helper classes which don't inherit from anything. Class-based views usually inherit from template view. So there you go. That's the difference. And the actual workhorse, so all the work is done here. And what we basically do is run a loop through all the decorators and try to find some combination of well-known names which we use in the project. And that's it, very simple. If these names do not exist, then error for the developer, go figure it out. That's the easy thing to do. So that's my last slide. Now, I told you this applies to other languages and tools. So for Python, Flake 8, I don't use Flake 8 that much, but I think it has the same capacity as Pylint. There's also a lot of plugins for Flake 8 available to download from PyPy. So if you're a fan of Flake 8 and use it extensively, you need to read a little bit more about it probably. But there is documentation how to create plugins for Flykate. It works with, it's again AST based. Bandit is for security related stuff. It is AST based. They have two types of plugins. Again, documentation is available. And if you don't use Bandit, by the way, you should use Bandit. It's very cool. If you go for Rubocop, for Ruby, it's again AST based, has information how to do stuff. If you try ESLint for JavaScript, it's again EST based, tells you how to do stuff. If you try Checkstyle for Java, if you try any other tool for any other language, they work in the same way. All the tools work in the same way. The actual architecture of these tools and how you structure your plugin or what the file name must be like or what interface you need to implement is of course different, but this is something which you can learn very quickly. I can tell you, for example, about Bandit, that when it was announced, I looked through the entire source code of Bandit, and everything that Bandit does can be implemented with the interface of Pylint. Why OpenStack decided to just create another architecture, I don't know, but it can be rewritten as a Pylint plugin. So, thank you very much. And if you do like to experiment and you don't have ideas on your own, just go to GitHub, search for issues with new linter. We have a lot of ideas for you if you want to contribute. If not, try to create a plugin for your team, for something which you have seen in your company and you know that this is going to be a problem. And now it's time for questions.